Good morning, everybody, and welcome to the CEIA Maths Tutorials online. In previous years, we've been running these tutorials for about 8 years now, and we used to run them on Saturday mornings in UCC. But due to the COVID this year, we have to go online. And we just want to say a few things just before we start and introduce the tutors. It's our first time doing these tutorials online, so we've got a fair bit to learn, so please bear with us when we make mistakes and things maybe not working exactly according to plan. We have our tutors, our maths tutors are all scientists, engineers who are actually, using maths in their everyday jobs, and they've got a passion for maths and they'd like to pass some of that on to you. As regards feedback, there will be some opportunities to give feedback about the tutorial at the end of the tutorial, just a few questions, and also during the tutorial you can submit a question to the tutors via the Q&A button, questions and answers, and they may not be able to answer straight away, but if we have enough time we'll get back to it, and maybe if there isn't time we'll try and do it by email or some other way like that. Now, I wanted to say that places are limited on the tutorial. We have a waiting list of more than 100 people, so if you're not interested or you don't want your place anymore, please tell us and we can give it to somebody who's on the waiting list. During the tutorial we'll have some breaks. I mentioned Q&A. There's also the possibility to raise your hand, and there'll be some poll questions coming along as well, just a couple, that you can just click the answers on screen. No, I'd like to today introduce you to the two tutors they're giving the tutorial today are Jerry Sweeney and Edmund Collins. And the first up, it's the introduction, and they're going to cover some essentials. And the first up today is Jerry Sweeney with his presentation about numbers. Okay, so Jerry, are you ready to go? Morning, Jerry.
Okay. All right. Okay, so thank you, Eamon, and welcome everybody. Delighted to have the opportunity to give an overview and introduction to this series of lectures. All the lecturers, all the presenters are professional engineers. We use math as part of our daily lives, and we want to help you to study for the Leaving Certificate, but we also want to share our enthusiasm for mathematics. So we don't see this as a grind situation. We're also trying to get across an enthusiasm to you. I love engineering, science and math, and I'm hoping that in the next 40 minutes, some of that love becomes obvious to you. In this lecture, I want to explain what math is and why it is so important. The other lectures that follow in this series will deal with individual specific topics. This lecture is an overview and will, in one respect, encompass all of mathematics. I feel very privileged to have the opportunity to give this introductory overview, and I thank CEIA for the opportunity to deliver this lecture, which I have entitled Math of Mathematics. So mathematics is a tool to help us to think and to solve problems. And when math is taught in schools, it tends to be taught as a series of academic exercises, gymnastics, mental gymnastics, and it's not obvious what the applications are. For me, sorry. For me, mathematics is something that I use in my daily life. It's something that's very live, and this is the idea that we want to get across. So technological advances, especially in the last few hundred years, are incredibly dependent on mathematics. Electricity and electromagnetic waves, computers and software, energy and transport are all areas that are underpinned by mathematics. And those are the areas that have changed our civilization more than anything else. In 1960, Eugene Wigner published a paper that describes the unreasonable effectiveness of mathematics in the natural sciences. And there is something fundamental about our universe that makes math able to describe and predict it. It's as if the world itself is a simulation based on mathematical rules. So to put mathematics in context, I have created this slide, and this is basically a map of my talk this morning. So we as humans, we work with concepts. So we have ideas, we have an understanding of the world around us. And young children are famous for saying why. And what somebody is when they're asking the question why, is they're looking for something to be explained in terms of something that they already understand. So concepts are the starting point of mathematics. We have to have an understanding of the world around us. And we start by looking at concepts from models that we can hold in our minds. That's the way we're going to start this morning. Then we will add numerical properties to these models. We can add other properties to the models as well as numbers, such as Boolean properties, true or false, or whether something is part of a set. But we're going to focus mostly on numerical properties. And once you start thinking in terms of numbers and become familiar with numbers, and numbers themselves become a concept in their own right. And we can think in terms of the number itself rather than what it encompasses. So we don't need to think in terms of 5 sheep as a real world concept. We can think in terms of 5 as a concept in its own right. But personally, I like to go back to the basis. You know, why do we have numbers and where do they come from, rather than treat them abstractly. So we're going to come back to that concept of abstract mathematics later again. So we will investigate how to manipulate numbers or other properties of these models. For example, using arithmetic operators, plus, minus, multiply, and divide, we can manipulate numbers. But we're going to start with models. And models are concepts. So a concept or a model is a framework where we allow something to be true. And the end of why is an aha. Ah, okay. You know, something that we understand in terms of something else. You know, why did Aunt Minnie go to the hospital? She went to the hospital because she broke her leg. You know, we understand that if somebody breaks their leg, they go to hospital, so we stop asking questions. If you didn't know what a hospital was, you would say, well, what's a hospital? So before we start on math, let's investigate how our brains can hold concepts. So this is a concept that involves logic, but does not involve any calculations or numerical properties, but it's an incredibly interesting concept. So let's explore thinking, okay, by trying to solve this problem or puzzle by pure thought. So this is a riddle, and I want you to sit back and relax and think about it for a second, okay? So a monk leaves his home in the valley early in the morning and walks to the temple at the top of a mountain, arriving at dusk. So he spends the whole day traveling from early morning till dusk. He spends the night in the temple, and early the following morning, he returns down the mountain path, following the same path, arriving home in the valley at dusk. So on the second day, he travels from the top of the mountain back down again. So first day, he climbs the mountain or he walks up the path. On the second day, he comes back down the same path. Can we prove that there is one point on the path that the monk was on at the same time on both days? Now, if you pick any point on the path, then you know the monk passes that point on both days. He passes every point on the way up, and he passes every point on the way down. But how do you prove that there is one point on the path where the monk was on both days at the same time? And a way of proving that to yourself is to imagine that there are two monks instead of one. One climbs on a day and the other one descends on that day. So these two monks would walk past each other at one and only one point. If we accept that one monk on 2 days is analogous to two monks on 1 day, then we can see that for the single monk, there will be a point that is traversed on both days at the same time. Now, I love this puzzle, and what's interesting about it is it simply creates an aha moment in your head. Aha, okay, so if it was two monks on 1 day, they would walk past each other, they would wave and say good day, and that proves, okay, that they were on the path at the same time on that day, and that being analogous to to one monk on 2 days is a proof that the monk traversing the path up and down on 2 different days does actually get to one point on the path at the same time on both days. And that's the way our brains work. They work on the basis of models. So there are things that we know about the world, and we can construct ideas and models based on that. So let's now add properties to those models. So that model was a pure thought experiment. Let's add properties. So the properties we're going to focus on are numbers, but we're also going to focus on maybe, or you could focus on Boolean properties like true or false, or set properties like intersection and so on. But we are going to focus mostly on numbers. So there's a picture in front of you here, and that represents something that we can think about. So some models have numeric properties. So whatever we represented the model in front of us, okay, has numeric properties, but it depends upon what model we're talking about. So what number would you associate with this picture? It could be 3 coins, it could be €3.50, or many other numbers depending on the model that we have chosen. So this is important. The model determines the properties. So if we're talking about number of coins, it's 3. If we're talking about the value of the money, it's €3.50. So the model or the concept determines what the properties are. We could also assign non-numeric properties to this photograph, okay, if we were looking at metal color. And we could use set theory to analyze, how many colors were in a particular coin. 2 of those would belong to the set that contains 2 colors and so on. But we're not going to go down that rabbit hole right now. We're just going to stick to numeric properties. So if we think in terms of this being 3 coins or €3.50, for 2 different models, and this gives us an idea of the properties that are involved. Okay. So how does this apply to the Leaving Cert? So one of my favorite, and I'll explain why in a moment, but one of my favorite problems on any Leaving Cert paper is question 9 on 2019's paper 1. And it's about Windows. So I need to explain one of the reasons why it's my favorite, one of my favorite questions. So many years ago, I was working as a software developer. And one of the projects I worked on was software to help manufacture aluminium windows. So the windows were rectangular in the software that I worked on. And depending on the size of the window and the style of window, was it the top opening, side opening, or whatever. So there were approximately 20 designs of window, and there were 2 dimensions then, 2 independent variables, the height and the width of the window. And my software was to take in a list of windows for a project, and then to produce a list of material that needed to be cut, the aluminium extrusions that needed to be cut to manufacture that. So for a house requiring 20 replacement windows with old houses, they would typically all be of different sizes. This resulted in a lot of error-prone calculation for the length of aluminium extrusions that need to be cut. So my software involved accurately calculating the length of the extrusions that needed to be cut to manufacture those windows. So, so this question, for a couple of reasons, that my talk this morning is going to be very focused on this question, and there's a couple of things that are nice about it. Okay, from a student's perspective, one is that it has about 5 parts in it, but in order for you to the next part of the question, it tells you what the answer to the previous one is, so you can check your work as you go along. So the only part that there's any danger that you'll actually make a calculation mistake and not be aware of it is the final part. So it's a really nice question from that perspective. So there's no reason why you can't get 100% of the points for this question. So, so the model here is a window, and the window has an arch on the top of it and has a rectangle on the bottom of it. So this is described in the question as being a Norman window. Now, I want to introduce the concept of independent variables and dependent variables. So in order to uniquely define a window in this shape, all we need to do is to define the radius of the circle on top and the height, because the length of the rectangle is clearly twice the radius. Sorry, the width of the rectangle is clearly twice the radius. So 2x is the base of the rectangle, as well as being the diameter of the circle. So we have 2 independent variables involved here. So in the question, they are defined as being x and y. Now, I'm writing with my finger, so the quality of the writing is not going to be great. Now, in the question, we're going to work on 2 dependent variables. And those dependent variables are going to be P, which is the perimeter of the window, and then the area of the window. So P and A are the dependent variables. We're going to create functions for P and A in terms of X and Y. Now, just to explain about independent variables, you could have a variable which would be the diameter of the circle or the base of the rectangle, and that would be a different independent variable. But since one is twice the other, they're interchangeable. So I suppose you could say, okay, that you can describe this particular window with 2 properties, and the examiner has chosen X and Y as drawn on the drawing as the independent variables. And they're going to ask us to work in terms of the dependent variables, P and A, the perimeter of the window and the area of the window. Now we're going to come back to this again. This is, I'm going to keep referring to this problem as I go through the lecture. Okay, so arithmetic is something that you learn as soon as you go to national school. You start learning your addition and subtraction, and then you get introduced to multiplication and division. And when you go into secondary school, you come across indices and logarithms. And these are the 6 arithmetic operators that you use in manipulating numbers. Right, so let's move on. One of the most interesting aspects of number systems is that throughout history, people have been inventing more and more types of number. And if you go back 2,000 or 3,000 years ago, people worked with natural numbers. Okay, I can see 1 cow, I can see 2 sheep, I can see 3 goats. And there was resistance in some cultures to the adoption of 0 as a number. We have no difficulty with 0 as a number today, but it's important to remember that it's possible for someone to have models in their heads that preclude 0 from being a number. So we have had the aha moment to say, well, if there are no apples in the basket, okay, then it can be represented by the number 0. So the first extension of natural numbers would be the extension out into whole numbers by adding 0. And then another culture would have come along and said, well, we don't agree with the concept of negative numbers. But if you use the subtraction operator, okay, then you can create negative numbers quite easily. And if you use division, you can create rational numbers. And something funny to tell you, okay, is when I was studying mathematics at your age, I thought the word rational, okay, meant something that there were sensible numbers and irrational numbers were not sensible numbers. It was only about 10 years later it dawned on me that the word rational simply means ratio. It's one number divided by another. But rational numbers can be created by division, and irrational numbers are numbers that neither terminate nor repeat. And it's obvious if you think about it for a while, okay, that irrational numbers must exist. If you had a random number generator creating digits going on forever, it would create an irrational number. And it's also very easy to prove, okay, that between two every rational numbers is an infinite number of irrational numbers. So in fact, most numbers are irrational, but you can extend the number system. And the real numbers are the superset, okay, of all the rational and irrational numbers. Now, the reason why I'm stressing this, okay, is because two new number types are added to the Leaving Certificate syllabus: imaginary numbers and complex numbers. So I'm going to come back to this again later. So the important thing to remember, the important takeaway from this slide, is that imaginary numbers and complex numbers are added to the Leaving Cert syllabus. And what I have here is a number of examples of calculations that extend the number system up to the 8 types in the previous drawing. So natural, whole, integer, rational, irrational, real, imaginary, and complex. And I have a concern. I have a daughter who was supposed to have sat the Leaving Cert this year and she didn't. And I have a concern that a lot of people, okay, would have stopped attending school in March, and you may be behind in terms of your understanding of concepts. So 2 concepts you're going to have to pick up on for the Leaving Cert are imaginary and complex numbers. And perhaps you could take it as an action to watch some YouTube videos to get those clear in your head, so that when your teacher in school starts introducing you to those number types, that you are that you already have the concepts of those ideas in your head. So I'm not talking about concepts at the moment, I'm talking about numbers, but I suppose numbers have a concept in their own right. So 2 new types are added: imaginary and complex numbers. Okay, so we have talked about the properties of models, and we've talked about arithmetic. And arithmetic for the Leaving Cert consists of 6 operators: plus, minus, multiply, divide, indices, and logs. And Ed is going to continue after me this morning by going through indices and logs to extend the arithmetic capabilities, your capabilities. So he'll go through that. What we're going to do now, okay, is we're going to talk about algebra. So algebra is dealing with unknown numbers called variables. So you might know some properties of something in terms of ratios or whatever, but you don't know the actual number. And it's also for dealing with functions, relationships between variables. And when we get back to the example we're using this morning, we're going to hit relationships between variables. So this will become, so typically you're dealing with a number that you don't know the value of, but you could also be dealing with relationship between variables. So in other words, both variables can change. So let's talk about our window again. You have 2 variables for our window, X and Y. And you can change them independently, but there is going to be a relationship between them. So we're going to look at a situation where the perimeter of the window is a constant. And under that circumstance, then there is a relationship between x and y. So it's not that there is one valid value of x. It is that for any value of x, there is a value of y. So a function is something that defines the relationship between variables. I came across this puzzle when I was about 14 years of age, and I spent 2 days thinking about it, and I eventually solved it. But I solved it using English and logic. And about a day after I solved it, I figured out that I could solve it using simultaneous equations in a couple of seconds. So, let's look at this puzzle and see. On the face of it, it looks like it's a kind of a logic. It's a bit like the puzzle with the monks, but in fact, it can be reduced to an extremely simple problem if you start introducing principles of mathematics. So let's take this puzzle. Alice is twice the age that Bob was when Alice was the age that Bob is now. Alice is 36. What age is Bob? Now it's intended to be deliberately confusing. And what I'm hoping to show in the next slide or two, okay, is that we can reduce that to something which is easy to understand. And this can be solved as a problem with four simultaneous equations. So let's have a look at how we might do that. So the first thing to realize is that there are 4 variables in this question. Alice is, Alice was, Bob is, Bob was. We're going to give them names, AI, AW, BI, BW. So we're going to forget about the English. We're going to forget about the mind twisting stuff. And we're just going to focus on reducing the problem to 4 variables. And let's see what happens when we try to write equations based on those 4 variables. So we have 4 equations. So Alice is twice the age that Bob was. We can write that down as A is equal to 2 times BW. Alice was the age that Bob is now. AW is equal to B1. Alice is 36. That means AI is equal to 36. And the fourth rule is interesting. The fourth equation is interesting because it's not in the problem. And what it says is that the age difference between what Alice is now and what Alice's age was is the same as Bob's age now to what Bob was. And we know this, okay? If you have a brother or sister that's younger than you, okay, the delta age, the difference in age between the two of you stays the same. So formula D is not in the question, but it is in our understanding of how age works. And without introducing the fact that the delta age between Alice and Bob stays constant, this problem is not solvable. Once we have this, it's very straightforward. Alice is given in the question. So Alice is equal to 36, and using A, we can immediately deduce that Bob was 18, and we can go on from there. Okay, to show that Alice was 37 by taking formula D and I, and the first, and that Bob was 18. I'm not going to go through it. It's actually trivial to do these calculations. And we end up, okay, with the answer to the question of Bob is, and Bob is 27. And when I solved this problem using logic, I wasn't 100% sure that my answer was correct. I was pretty sure, but I wasn't 100% sure. But a day later, when I reduced it down, okay, to simultaneous equations and solved it this way and could see it written in front of me, then I knew, okay, I was very certain that I was correct. So I started this talk, okay, by saying to you that mathematics is a way of extending your ability to think. You can add properties to models, and then you can manipulate those properties. And in my opinion, this is an example of a problem that is very difficult to solve without mathematics, but becomes very simple once you understand how to apply those principles. We're back to Windows. So we're asked to write down the perimeter in terms of X and Y. And that's relatively easy to do. Just want to point out something here. Pi is not a variable, it's a constant. So it's just a number. Personally, I would prefer if we were asked to write P in terms of X and Y, and we're allowed to use the symbol pi rather than put in the number, but it's not a variable. But let's do this very simply, okay? So P is equal to, the perimeter is equal to, so we have two Y's plus two X's, and we have a half a circle on top. So that's pi r, because the circle is 2 pi r, so it's going to be pi r. And the radius here is x, so it's pi x. And we've solved it. So what we've done now is we've derived one dependent variable from two independent variables. And that's the first part of the question. And I was saying earlier, a nice thing about this question is when you move on to the second part, they give you the first part, okay? So in a particular Norman window, the perimeter P is equal to 12 meters. So what's going to happen now is the perimeter is going to be defined. And when the perimeter is defined as 12, we can actually then find a relationship between X and Y. So you can imagine that as Y increases, X will decrease, and as X increases, Y will decrease, because we have a certain perimeter around the window. So I want to put on my engineer's hat for a moment and talk about this problem from an engineer's perspective. So if you were manufacturing a window, let's say you wanted to get, okay, so the architect had said, I want a Norman window. I know they're hard to manufacture, but I want a Norman window. But you as an engineer then are tasked with getting the maximum amount of light through that window for a particular cost. So you want to make the window as large as possible, okay, for a particular cost. Well, the cost of glass is going to be a function of the amount of glass. So the bigger the window, the more glass is needed. But the perimeter is different. The shape of the glass has the shape of the window has a dramatic effect on the amount of material you need to put into the perimeter. So if you want to reduce the cost of the window, then what you need to do is to reduce the size of the perimeter. And what we're going to get to by the end of this problem, okay, is we're going to try and figure out what's the shape of the window to get the maximum amount of light through the window for a given perimeter. So all we need to do to solve this problem is to plug in 12 into what we had before. So if you look at the screen we had before, we had 12 is equal to 2x plus 2y plus pi x. So that's written down here again. And we just bring y around to the right side. We do a little bit of manipulation, and hey presto, we end up with A2 solved. I'm going to leave this with you just to think about for 30 seconds. Make sure you go through those 4 steps. So the top line of the 4 calculations is what we have on the previous screen. And then we just move the y to one side because we want to end up with something y equals. We do a little bit of manipulation. We bring the 2 across in order to go from 2y to y, and we end up with exactly the format that was requested in the exam paper. We're going to go on to something interesting in a second, okay? But if you take a look at for x less than or equal to, sorry, for 0 less than or equal to x less than or equal to 12 over 2 pi, down at the bottom there, that's interesting because, and we're going to deal with that in a moment, but it's impossible for x to be less than 0 because I don't know how to manufacture a window that has the side less than x. And That's going to come up on the next page. So what they're asking us to do here, okay, is to complete the table. So for a variable x, we have a formula giving us y. So what we now have to do is we have to plug in the value for when x is equal to 0. Now, if x is equal to 0, then it simply becomes 12 minus 0 over 2. So the answer there is going to be 6. And if we have 12 over 2 plus pi as being the value, then we have 12 minus 12 over 2 plus pi. The 2 plus pi's cancel out, and we end up with 0. So the table is filled in by putting in the values 6 and 0. Take a moment to get that clear in your head. Okay, so the next step of this question is to, on the diagram, draw the graph of the linear function y is equal to 12 minus 2 plus pi times x over 2. Now, they tell us it's a linear function, so we know we're going to draw a straight line. And we have 2 points on that line. Now, what I've done is I've calculated, using a calculator, what 12 over 2 plus pi is. And it comes out to be 2.334. And the reason I've done that is because we know that this line crosses the x-axis where x is equal to 2.334, and we know it crosses the y-axis where y is equal to 6. So I'm going to try and draw this as best I can. So I think I'm not quite far enough on the x-axis, but you get the general idea. So all you have to do is to draw a straight line like this. And it should intersect the x-axis at 2.336, and it should intersect the y-axis at 6. So what this is telling us is that if the perimeter is constant, then there's a linear relationship between x and y for a constant perimeter. So just because my drawing isn't great, I've put it in correctly here. The next step in this question is to find the slope of the line. And the formula for that is y2 minus y1 over x2 minus x1. You will do that in the geometry of the line, which is a lecture which will be coming up in the future. But the slope here is obviously negative because it's dipping down. And the value comes out to be minus 2.57. Now, in the question, they ask you for an interpretation of that slope in terms of in the context of the question. Now, I lifted the interpretation, okay, from the marking scheme, and I would encourage you, okay, to think carefully about the way they put this, because their interpretation is actually beautifully elegant, and it's a good pattern on which to develop interpretations. I always worry about interpretations because they are open to opinion, whereas minus 2.57 is not open to opinion. So it's worth thinking a little bit about this. For each 1 meter rise in the radius of the semicircle, the height of the rectangle falls by approximately 2.7 meters. Sorry, there's a mistake in my notes. That should be by approximately 2.57 meters. My apologies. So as for each 1 meter rise in the radius of the semicircle, the height of the rectangle falls by approximately 2.57 meters. Now, the next question introduces a function of the dependent variable area of x. And it, again, in this question, they give you the answer and they ask you to derive it, which is very handy because if you make a mistake, you know in advance that you've made a mistake. So the area is easy to figure out. Okay, so we have 2x along the base, and we have y along the height. So this area is 2xy. And then we have pi x squared up here. And because it's a half a circle, it's divided by 2. So a is equal to 2xy plus pi x squared over 2. And all we need to do now is to substitute in y so that we end up with a as a function of x. So we take the formula that we were given, or that we derived earlier, this guy here, and we plug him in for y. And we're off. So the rest of it, again, is simplification. And the beauty of this is they give you the answer. So I'm terrible at making mistakes in arithmetic and in solving algebraic equations. So I love it when somebody gives me the answer. So if you get it wrong, you can go back and fix it. But that's simple reduction. Okay, so what we've done is we've looked at algebra and we've seen how powerful the techniques in algebra are. We dealt with a puzzle around Alice and Bob's age, and we started work on an exam question around windows. And we looked at ratios between the independent variables, and we started introducing dependent variables, area and perimeter. With arithmetic and algebra under our belts, we can begin to study powerful techniques now that go on to solve problems. And many of these techniques were introduced in the junior certificate, so the leaving certificate is really a continuation of the study of those techniques. So the leaving cert extends your understanding of those techniques. But some new ones are being added, just like we mentioned that there were 2 new number types added on the leaving cert. There are some new techniques added as well. So a technique is, techniques like, actually let me go back and list some of them, okay? So cryptography, geometry, linear algebra, matrices, set theory, statistics, trigonometry. So these are techniques that use numbers and arithmetic in particular ways in order to solve particular sets of problems. What's really fascinating about mathematics is that a particular technique can be used to solve more than one problem. So here's an example. Exponential functions can be used to solve exponential functions can be used to solve problems around the spread of COVID-19 viruses, but it's the exact same mathematics, okay, that calculate mortgage interest rates. So I can't imagine 2 areas that seem on the face of it to be so different, but nevertheless, it is still the same. So one thing I want to say here, okay, is that some mathematicians work on mathematical techniques without ever considering uses for their work. This is often referred to as pure mathematics, as distinct from applied mathematics. And often it comes as a complete surprise when a use is later found for something that was initially considered as pure mathematics. So when George Boole of UCC fame worked on Boolean algebra around the middle of the 19th century, he didn't expect that his work would lead to computation 100 years later on. And I think probably everybody watching this video has a smartphone in their pocket. Mine rang earlier, sorry. So he didn't expect that it would lead to the smartphone revolution. So the application of mathematics by pure mathematicians, surprisingly often, something that's studied, okay, as a pure theoretical concept, turns out to have incredibly useful capabilities later. And this is one of the surprising things about mathematics. It's as if the world follows mathematics rather than the other way around. And as I mentioned, the technique, okay, in one area can be used in another area. I've given one example there. Okay, so we are talking about techniques now, but I decided to put the numbers back in here as well. So there are 4 things that are added to the Leaving Cert syllabus that are not covered at all in the Junior Cert syllabus. So because I'm a great believer in concepts and aha moments, I would encourage you to do some research, Khan Academy or YouTube or whatever is your favorite choice, to study extensions to the number systems that you have to deal with for the Leaving Certificate. They would be imaginary numbers and complex numbers, and the two are related. A complex number is a real number added to an imaginary number. And then calculus, and there are 2, just like there's plus and minus, multiply and divide, calculus comes in 2 flavors, differentiation and integration. So if these 4 concepts are new to you, I'm not surprised, but you will have to deal with them, okay, for the Leaving Cert. And it's a good place to start getting your concepts right on these, so that when you meet them in school, they won't go, oh my God, what's the teacher talking about? Now, I know I'm talking about techniques, but I wanted to bring all the new stuff on the Leaving Cert together. So I've actually brought imaginary numbers and complex numbers up here, which is probably the wrong place in the slide deck to put them. But you almost touched on imaginary numbers for the Junior Certificate, and you probably came across them in 5th year as well. Remember when you were solving quadratic equations? I think every student in the country can rattle off minus b plus or minus the square root of b squared minus 4ac all over 2a. And you were told, okay, that if b squared minus 4ac was negative, okay, you couldn't proceed. So the word there was, if the discriminant is negative, it can't be solved. Well, it can. If you allow square roots of negative numbers, and imaginary numbers appear on the scene, okay, when you allow square roots of negative numbers. Now, if you go back a couple of thousand years ago, you would have had people arguing that there was no such thing as negative numbers. And you know, you can't find an imaginary number of apples, but there is a number which has the unfortunate name of being imaginary, and you can manipulate it in arithmetic. But it's where you have a square root of a negative number. So imaginary and complex numbers, okay, so they appear in mathematics because of the inability to find roots of negative numbers. And there will be 2 lectures on the whole area of imaginary and complex numbers later in the course. So today is just a hello, don't worry about it. So the solution is to define the square root of -1 as being I or iota. And you may have heard the phrase, I haven't an iota. And that comes from that mathematical use of the Greek letter I, iota. Now you can portray any other number then as being, any other imaginary number as being a multiple of I. So the square root of -1 of -9 is equal to the square root of 9 multiplied by the square root of -1, and that's equal to 3i. So I and multiples of I are called imaginary numbers. And then a number can have a real and a complex part, and we write them as a plus ib. So the real part is a, and then you have the imaginary part b. If this is your first introduction to them, all I want to do is to make you aware that they exist, and it's a good time to start looking at Khan Academy and YouTube. And they are confusing. You need an aha moment. But I do want you to remember one thing. They have nothing to do, even though there's 2 numbers, A and B, they have nothing to do with Cartesian coordinates of geometry, anything like that. This is a single number. So A plus IB is a single number, which has a real part and an imaginary part. It's not 2 numbers. And what is amazing about imaginary and complex numbers is that all of arithmetic works. So the 6 arithmetic operators, plus, minus, multiply, divide, exponent, indices, they all work perfectly with complex numbers. And I've done here, I've added them together. To add together, you add the real parts and you add the imaginary parts separately. When you multiply them, you use the fact that I squared is equal to -1, and you end up with, so if you multiply 5 plus 3i by 3 minus I, you end up with a new complex number, which is 18 plus 4i. And you can actually multiply 2 complex numbers together and end up with a real number. And all of mathematics hangs together. And one nice thing you will like to hear, okay, is that there are no more numbers. Once you do imaginary and complex numbers, we can't use an arithmetic operator to create a different kind of number. When you go to college, you will come across hyper complex numbers, which are just bigger versions of complex numbers, but you can't generate them automatically from arithmetic. So once you do imaginary and complex numbers, you're done. Okay, you're home dry. All right, and again, I'm assuming that the vast majority of people haven't come across calculus, and calculus is a technique. It was invented in 1 year by Isaac Newton. A bit like now with COVID-19, he was in Cambridge, he was about 22 years of age, and Cambridge was shut because of I think it was the Black Plague, and he went back home for a year, and he was about 22 years of age, and he invented calculus as a 22-year-old at home. And in later life, he published a book called Principia Mathematica, and everybody said, why didn't you tell us about these techniques that you had before? And he went, I thought everybody knew them. He just thought they were so simple and straightforward. So this guy invented calculus, differentiation and integration. And differentiation and integration are opposites of each other. If you differentiate something and integrate it, you end up back where you started from. And I'm going to just give you a flavor of calculus and why it's so powerful. And we're actually going to use a tiny bit of calculus to finish solving that problem that we started with the windows. And yes, I do have a fascination with windows. Okay, so this is my headache slide. I don't want you to get upset or excited. I can see people tuning out all over the country. So I have 3 kids, and I taught them all about differentiation and integration while driving my car. So I want you to imagine something. So imagine you're a passenger in a car and you have a sheet of paper and a graph paper, and you're going to, on the x-axis, you're going to have time, and on the y-axis, you're going to have speed. So every 10 seconds, you look across at the speedometer and you say, we're doing 30 kilometers an hour, we're doing 35 kilometers an hour. And you draw a graph of speed versus time. It mightn't be immediately obvious, but the distance you travel is the area under the curve. And the acceleration, whether you're being pushed back into your seat or not, is the slope of the curve. So the rate of change of acceleration, the rate of change of speed is acceleration. Now, if you're doing maths, physics, and applied maths for the Leaving Cert, then by the time you get to the end of this year, this drawing will make perfect sense to you. But don't worry if it doesn't, okay? So what you have is you have 3 graphs there, so you have acceleration. So you could think of it as being a train on a very smooth track, or you could think of it as being a spaceship out in space. So if we start at the bottom with the acceleration, you have forward acceleration, which causes your velocity to increase. Then you have no acceleration. Then you have reverse acceleration, which is slowing down. Eventually, because you're accelerating in the opposite direction, you start going in the opposite direction, and then you accelerate forward again. And so the bottom one is acceleration, the middle one is velocity, and the top one is distance traveled. Don't worry about it. If this is confusing for you, it's fine. So Newton, when he was working on calculus, he was working on solving problems in this space. But it is probably the most applied technique in all of mathematics, certainly in engineering mathematics. So if you go on to do any science subjects, including biology, bio, anything, you will end up doing a hell of a lot of calculus. So the Leaving Cert introduces you to this incredibly powerful technique. Now, we need one part of calculus to finish our problem. And what we have here is we have a function which is a parabola, which you'll be very familiar with, which is drawn here and is labeled f of x. And then we've got f dash x. Something I want to actually tell you, which is interesting, is when Isaac Newton invented calculus, another guy in Eastern Europe, I think his name was Leibniz, invented calculus as well. And they used 2 different notations. Newton's notation was this f dash notation, and Leibniz used the thing called dy dx. And most of the time, we use dy dx, which is, I'm getting them mixed up now, which is Leibniz's way of writing it, but this happens to be Newton's way of writing it, but they're identical. So if you notice that there are two notations, it is because there were two independent developers. Newton's one is shorter to write, but Leibniz's one is probably more descriptive. Okay, but here's the point. Here we have a function, okay, f of x, and we have the differential of f of x. So what the straight line is there is a function which is actually the slope of x. Now you will notice that the slope goes to 0 at the maximum, and that means, okay, that f dash x, which is the function of the slope of x, passes through the x-axis, has a value 0 where that occurs. That means that differentiation can be used, okay, to find maxima and minima. So I'm going to read out what's on the slide. The maximum and minimum points on a curve are identified by a slope of 0. Therefore, wherever the differential of a function is 0, it's either a maximum or a minimum. So, okie dokie, we have to finish off our problem. And in order to finish off the problem, we have to have a little bit of differentiation in this case, because the problem is find the ratio of x and y that maximizes light through the window for any expenditure on the peripheral metal. Now, I'm taking poetic license here. The question in the exam paper doesn't talk about minimizing expenditure and maximizing light. It's just being an engineer, you know, I don't want to be told to do something academically for the sake of it. I want to actually do something which has got a benefit. So what we have here is, we already found the formula for A of x, and we're not going to do how to differentiate that formula, but that formula is so simple that anybody who has done differentiation can actually differentiate it on site. Trust me on that. There's a very simple technique for going from A of x to A dash x in this incredibly simple case. And it turns out that, so the A of x is a parabola because it's got an x squared in it, and A dash x is a straight line. So that means it equates exactly to the graph we have before. And what we can then do is we can say that for a maximum, A dash x, so I've gone from the red box now to the green box. So in the green box, okay, we set A dash x equals to 0, and we find that x is equal to 12 divided by pi plus 4. Now, what's really bizarre here, and I absolutely adore this, is if you now go on to calculate y, so we know what x is, we know what the peripheral is, therefore we can calculate what y is. And what turns out to be absolutely mind-blowing is that x is equal to y. So think about this. If you're an engineer and you're tasked with the job of defining what shape that window must be in order to get the maximum amount of light for the minimum cost in peripheral metal, the answer is x is equal to y. So we spent half an hour calculating it and it came out of that. Now, okay, if you find that fascinating, then you're me, okay? And if you don't, then you're not me, okay? But as an engineer, you know, getting an answer like x equals y is amazing. And when I saw this answer, first of all, I spent ages trying to figure out why is that the case. And I actually did kind of get an intuition for it. The semicircle on the top a circle is the most efficient shape that you can get in terms of maximizing the area against the peripheral. So all you're really doing is you're maximizing the rectangle, and it works out okay because the rectangle is now three-sided because there's a hemisphere on top. It works out that x equals y, where x is half the base, is the most. So after looking at it for a while, I got an intuition as to why it would be good. Okay, so we're going to summarize. So what we've done there in the end, okay, is we saved ourselves a load of money by designing Norman windows, okay, where the radius of the circle on the top was equal to the height of the rectangular bit. And that can be applied in chemistry, economics, engineering, you name it, okay? And I've looked at the syllabus and looked at exam questions on the Leaving Cert, and I'm in business, I'm the managing director of a company, and the financial questions, the financial mathematics questions on the Leaving Cert are absolutely fantastic. And I would encourage you to, depreciation and mortgage interest and so on, I use them every day. So it's not just engineering, okay? And I love using math to solve problems, and my interest is in applications. Everything from quantum mechanics, okay, to relativity is of huge interest to me. And can I finish by suggesting that Elon Musk is the most influential person on the planet today. He created PayPal, he runs Tesla, he's chief engineer of SpaceX, taking us to the moon and Mars and beyond, while delivering broadband through the Starlink thing as a sideshow. He's involved in artificial intelligence. This week, if any of you were watching the news, okay, he had a pig with a neural implant. He's involved in the Boring Company, and he and some of his family members have a solar operation called Solar City. Now, okay, it's my opinion, and other people may have different opinions, but he certainly is one of the most influential people. And he's not influential because he's an artist or because he's a philosopher. He's influential because he's an engineer, and he lives by calculation. Everything that he does is calculated. And I would put it to you, okay, that the future of our species, for the future of our species, mathematics, science, and engineering will play an ever-increasing role. If we're to solve the problems we have around climate change, etc., then we have to produce more and more scientists. I would like to thank you for taking the time to listen. I believe I've gone 5 minutes over time, but I'll just hand back to Eamon now, please.
Thank you, Jerry. Thank you very much for that very clear and interesting presentation. Hello and welcome back to the introduction tutorial for the CEIA Maths. We've had Jerry Sweeney in the first part, and for the second part of the tutorial, we've got Ed Collins, who is a mechanical engineer with a lot of experience in the pharmaceutical industry.
Good morning, everyone. Thank you, Eamon, for the introduction, and also to Jerry for that very interesting first tutorial. And I'll be referring back to some of the concepts and principles that Jerry went through in the tutorial. Just a little bit about myself. As Eamon mentioned, I'm a mechanical engineer, chartered engineer. I've worked in the pharmaceutical industry, but I've worked in roles as diverse as maintenance, management, engineering systems, energy, and utilities management. This morning, I'm very pleased to give you this tutorial on indices and logarithms, or otherwise known as logs. Now, indices and logs are used extensively in mathematics, but also out in industry. And I've used indices quite a bit when I'm doing calculations, particularly when I'm converting from, let's say, millimeters to meters, that type of thing. I'm using different dimensions. So I have used indices quite a bit, and certainly if you're going to do engineering, indices comes in there quite a bit. I may not have used logs directly in my working day, but I would have used them indirectly. As you see, they're used to generate the pH scale, decibel scale, and so on, which I have used in my engineering work. So indices and logs, they're two sides of the one coin. It's very important that you're comfortable with indices before you move on to logs. If you can work well with indices, then you will be able to manage logs very well too. So we'll start off with indices, and you see there's an index statement there, 2 to the power of 3 equals 8. So what do these all mean? Well, 2 is referred to the base of the index, or sorry, of the statement, and then 3 is the index, and 8 is the value of the power. Now 3 can also be referred to as the power. So 2 to the power of 3, we often talk about that. So what does that mean? Well, it really means that we're talking about 2 by 2 by 2. So 2 multiplied by 2 is 4, and then 4 by 2 is 8. So there are a number of laws that apply to indices. There are 8 laws that I'm going to go through with you this morning, and then we'll move on to logs. So the first law, so if we're multiplying two powers there together, 2 to the power of 3 multiplied by 2 to the power of 2. If we write this out longhand, just to explain the concept, 2 to the power of 3 is 2 by 2 by 2. 2 to the power of 2 is 2 by 2. So we end up then that we have actually 2 to the power of 5, as you can see there on the slide. So from this we can derive that 2 to the power of A multiplied by 2 to the power of B equals 2 to the power of A plus B. That's very important. It's not A multiplied by B, it's 2 to the power of A plus B, as we've seen in the line above. So that's the first law in relation to multiplication in indices. So what happens if we divide 2 powers, so 2 to the power of 3 divided by 2 to the power of 2. In this case, 2 to the power of 3 is 2 by 2 by 2. It's divided by 2 to the power of 2, which is 2 by 2. And we end up with 2. Now, you see I've written there 2 to the power of 1. Now, we don't often write numbers, we don't write them this way, but in terms of indices, it's implied that a number without an index or power is actually to the power of 1. So the second law, therefore, is 2 to the power of A divided by 2 to the power of B equals 2 to the power of A minus B. So that's the second law of indices. Moving on to the third law. Now this is a bit tricky and not to be confused with the first law. This is a situation where we're raising a power to a power. So it's up to another level, if you like. We have one level, 2 to the power of 3, and we're raising that to the power of 2. Again, to help us understand this, it's good to write it out. So 2 to the power of 3 is 2 by 2 by 2, and we're going to multiply that by the same again, because it's 2 to the power of 3 squared, if you like. So when we look at that, then we see that we end up with 2 to the power of 6. So therefore, the third law means that 2 to the power of A, which is raised to another power B, equals 2 to the power of A multiplied by B. So again, not to be confused with the first law. So just watch out for that if you're doing questions that you see a power raised to the power, and we'll be looking at more examples of these later on. Now here's an interesting little law. What is 2 to the power of 0? So Jerry was talking about 0, and some people didn't even want to call it a number, but it certainly is in this case. Well, 2 to the power of 0 equals 1. Now, when I started doing the tutorials, I was trying to work out a way of proving that to myself. Why is 2 to the power of 0 equal to 1? So then I went back to one of the earlier laws and said, well, 2 to the power of 0 is equivalent to 2 to the power of A minus A. And again, using the law for division, I saw that 2 to the power of A minus A was 2 to the power of A divided by 2 to the power of A, which equals 1. Just be careful as well. Some of these laws, particularly the early ones, the multiplication and division, when you're using those laws, you have to be working in the same base. So those laws, you know, if you're multiplying 2 to the power of A by 2 to the power of B, that's fine. But if you're multiplying 2 to the power of A by 3 to the power of B, then you see, if you work it out yourselves, that law wouldn't apply. So it's just very important in some of the laws, you must be in the same base. And actually, when we get onto logs, it's very important that we work in the same base. In this case, we're just dealing with one number, and any number to the power of 0 will be 1. And we'll come back to that in logs again. That's just important to remember. Any number to the power of 0 equals 1. So the fifth law, so what happens if we have 1 over 2 to the power of A? Well, again, using our previous law, 1 is 2 to the power of 0, and that's over 2 to the power of A. And from our other earlier law for division, we see that that's 2 to the power of 0 minus A, so that equals 2 to the power of minus A. And you may say, why go to all this trouble? But again, I found in calculations, working with dimensions and so on, you may have something newtons per meter squared, for example. If any of you have done physics, you'll have come across this. When you're working with those dimensions and you want to simplify things, it's important that you bring it all up onto the one line. So that's where the minus will come in indices. And then likewise, if you had 1 over 2 to the power of minus A, that's equal to 2 to the power of 0 divided by 2 to the power of minus A. And that equals 2 to the power of 0 minus A. So the two minuses will cancel out, and that equals 2 to the power of A. So likewise, we've looked up to now, we've just looked at numbers, but as Jerry was doing in the first tutorial there, we're often dealing with variables x, y, whatever, dependent, independent variables. But in this case, if we had an equation where we had 1 over x to the power of minus 2, well, again, x to the power of 0 is 1, and 1 over x to the power of minus 2 is equal to x squared. Again, very important, you may come across some equations where the information is presented in this way. So the sixth law, so if we have the square root of x, that equals x to the power of A. Now we know from the previous law that square root of x multiplied by the square root of x equals x to the power of 1. So therefore, x to the power of A multiplied by x to the power of A equals x to the power of 2A. We can derive from this that 2A equals 1 and A equals half. So therefore, it's just another way of writing the term square root of x. That equals x to the power of half. Because again, if you're working with equations, you want to simplify things, you need to get everything into the one format, as it were. So rather than dealing with square roots of x and so on, if you're working with a number of indices statements, then you can use this form for the square root of x, x to the power of half. And if we look at the example at the bottom of the slide there, 4 to the power of 3 over 2, how would we evaluate that? Well, again, we can say from our previous law that 4 to the power of 3 over 2 is 4 to the power of a half to the power of 3. So then it's easy to actually get the square root of 4. In this case, 4 to the power of half is 2. And then 2 to the power of 3 is 8. So what might look like quite a difficult thing to calculate when you simplify it in this way, turns out to be quite easy in the end. The seventh law, if we have two variables inside the brackets, x multiplied by y to the power of n, that equals, or is equivalent to x to the power of n multiplied by y to the power of n. And then in the eighth law, similar, except we have x divided by y inside the brackets to the power of n, and that equals x to the power of n divided by y to the power of n. Again, will be used in problem solving. So I hope that's given you some introduction to indices, how they're used, and you can see that some laws depend on previous laws and so on. Just once, it's a bit like what Jerry was talking about, you know, early on, when we start off with maths, we're doing quite simple addition, subtraction, multiplication, and so on. Similarly with indices and logs, we start off with these rules, but they become second nature, and the more you use them, the more familiar you are with them. But it is important to get the foundation right. That means you can move on and work with more complex problems. So here's an example. You know, how would we simplify this equation here, where we 3 to the power of 5 minus 3 to the power of 3 equaling x? Well, again, from our law, we know that 3 to the power of 5 equals 3 to the power of 2 multiplied by 3 to the power of 3. Remember, that is a plus b there. And if we take out 3 to the power of 3 outside the brackets, we're left with 3 to the power of 2 minus 1 multiplied by 3 to the power of 3 equals x. Simplify inside the brackets. 3 to the power of 2 is 9, minus 1 is 8, and therefore we're left with x is equal to 8 by 3 to the power of 3. So that's just one example of using indices to simplify an index statement. So here's something you might try. I'll just give you a minute or two to try this. So it's quite similar to the previous example. So here we have 2 to the power of 7 minus 2 to the power of 6 equals x. So how would we simplify this to calculate x? I'll just give you a minute there. So, as I said, quite similar to the previous example. 2 to the power of 7 is 2 to the power of 1. I haven't written in the 1 there, but it's implied. Multiplied by 2 to the power of 6 minus 2 to the power of 6 equals x. Again, we take 2 to the power of 6 outside the brackets, and we're left with 2 minus 1 by 2 to the power of 6 equals x. 2 minus 1 is 1, so x equals 2 to the power of 6. Now here's another example. A little trickier, this one, because the index, our power in this case, is 2x minus 1. But it shouldn't really worry us too much. We're dealing in powers. It's a power. But what's important here is that 81, we need to get it into the same base as the left-hand side of the equation. So when we look at this, we see 81, 9 nines are 81, 3 squared is 9, so we can see 3 to the power of 4 equals 81. Once you have it in that format, then you can say that the indexes are powers on either side are equal to one another. So this is a technique that's often used, and you'll see this coming up in logs as well. But they have to be in the same base. You have to be working in the same base either side of the equation. That's very important. So in this case, we can see 3 to the power of 2x minus 1 equals 3 to the power of 4. Therefore, 2x minus 1 equals 4. And working through the algebra, x equals 5 over 2, or 2.5. Now here's another question for you to try. 2 to the power of 3 to the power of x equals 2 to the 4. 2 to the power of 4, sorry. Find x. Now remember, this is a power to a power. So just be careful with that one, but it's quite straightforward. In this case, we have the same base on both sides of the equation. So at least we don't have to do anything with that. So I'll just give you another minute there to try that question. So here's the solution. 2 to the power of 3 to the power of x is 2 to the power of 3x. Remember our law there, where we multiply 3 by x, and that equals 2 to the power of 4. Again, both sides of the equation, we have the same base 2, and therefore we can say that 3x equals 4. The power index on either side are equal to one another. And from that, we can derive that x equals 4 over 3. So nice little problem there. So that's the first part of the tutorial on indices. So having worked through indices, now we'll move on to logs. And as I say, this is the other side of the same coin here. So we saw the index statement 2 to the power of 3 equals 8. Well, now that's equivalent to saying that the log of 8 to the base 2 equals 3. So we can also write a log in the form where 8 can be written as 2 to the power of 3, 2 by 2 by 2. So that makes it somewhat easier now when you see it written that way. So the log to the base 2 of 2 to the power of 3 equals 3. So I like to look at logs that way. So you can see the base is the same as the part of the index, the base of the index, if you like. And therefore the log falls out of that as 3. So in this case, the base is 2, the value is 8, and the log is the index, which is 3. Now this technique for evaluating a log I've taken from Aidan Rowntrie's maths book, Effective Maths. So it's not my technique, just want to acknowledge Aidan's book there. So in that he said method to use would be let the log be equal to x, write the log statement in index form, and then solve the equation for x. Now, before we go on to look at logs in more detail, there's a number of things we should be aware of. Common logs, as they're commonly called, are logs having a base of 10. So when logs were first introduced, I think it was to do with navigation and so on, the logs used at that time would have been base 10, so it was quite common. They were the common logs. But there are natural logs as well. Now they're just logs to a different base. So they're the logs, natural logs are to the base E. So we saw in Jerry's presentation, he brought up E. It's an irrational number, approximately 2.718, but it goes on 2.71828 and so on. So that's it. If you see a statement, the form of E, and you want to convert it into logs, well, then you would use natural logs. But in the questions in the Leaving Cert and some of the examples we'll be going through a little later, they've had logs to the base 3 and so on. So different logs can come in, so it won't just be common logs or natural logs. So logarithmic scales are used for measuring pH in chemistry. Any of you studying chemistry, we're quite familiar with pH. So that's a logarithmic scale. And the strength of earthquakes as well, the Richter scale. You often hear that mentioned in relation to an earthquake. Logs are also used in the calculation of decibels, which are used extensively in acoustic and electronic engineering. So they come up quite a bit across engineering and in other areas as well. So here's an example, going back to the methods that we looked at earlier. How would we calculate the log of 1,000 to the base 10? So we write it out this way. Log of 1,000 to the base 10 equals x. 10 to the power of x equals 1,000, which is equal to 10 to the power of 3. Therefore, x equals 3. So the log of 1,000 is 3. Again, if you were to write it out in the form of log to the base 10, 10 to the power of 3, that would help you. Then you would see that straight away. Then that the log is 3. So here's one that first looks a bit tricky. We're dealing now in the base 8. We want to find the log of 32 to the base 8. Again, we can write it out. Log of 8, our log of 32 to the base 8 equals x. 8 to the x equals 32. But that's difficult now because we haven't the same basis either side. So we can simplify 8 to the x. We can convert 8 into the power of 3, and then 32 to the power is 2 to the power of 5. So therefore 2 to the power of 3x equals 2 to the power of 5, and again same base, so the indexes our indices and are equal. So therefore 3x equals 5, x equals 5 divided by 3. So here's another little question for you to try. What's the log of 9 to the base 3? I'll give you a hint there. We need to write 9 in the form of 3 to the base 3. So I'll just give you a minute to try that question. Well, log of 9 to the base 3 equals x. 3 to the x equals 9. 3x equals 3 squared, which is 9 again. Both sides of the equation is the same base, so x equals 2. But again, as you become more proficient, you could have looked at the statement log, the log of 9 to the base 3, and you could have converted 9 into 3 squared, and then you would see, oh yes, the number, both bases are the same there, and the log is 2. So we'll go on to more laws or rules around logs. Sometimes, you'll see people referring to 3, 4 laws of logs. I'm actually going to go through 7 laws, but people differ in terms of the number of laws. But it doesn't really matter that, in terms of the number of them. What's important is how they're used. And you'll also see that the first couple of logs are very similar to the laws of indices. So again, you see that coming through. So in the case of x multiplied by y, so the log, the base a of x multiplied by y, that equals log of x to the base a plus the log of y to the base a. So if we were to put numbers into this, so let's say we input 4 for x and 8 for y. In that case, then the log of 4 multiplied by 8 to the base 2 equals the log of 4 to the base 2 plus the log of 8 to the base 2. And if we were to calculate that out, that would be the log of 32 to the base 2. So 32 is 2 to the power 5. So the log of 32 to the base 2 is 5. And that equals the log of 4 to the base 2, which is 2, plus the log of 8 to the base 2, which is 3, because 8 is 2 to the power of 3. So that just proves the law there, just working through it. So that's the first law. These laws are used in the Leaving Cert questions. So again, you'll have to be quite familiar with them and know when to use them as well. So that's the first law. Second law is to do with division. So in this case, if we had the log of x divided by y to the base a, that equals the log of x to the base a minus the log of y to the base a. So you'll see the similarity there with the indices. So again, inputting 8 for x and 4 for y into the equation, we get the log of 2 to the base 2 equals the log of 2 to the log of 8 to the base 2 minus the log of 4 to the base 2. Now the log of 2 to the base 2 is 1. So remember, 2 is actually 2 to the power of 1. So again, that proves that second law, 1 equals 3 minus 2, which is 1. Third law, again, used quite extensively and very, very useful for solving problems. If you have a situation where you have log of x to the base a, log of x to the power of n to the base a, then that equals n times the log of x to the base a. So we had the situation where we had the log of 4 squared to the base 2. That is the same as 2 times the log of 4 to the base 2. And working it out there, you can see if we convert 4 to 2 squared, you can see working through the logs there, that 4 equals 4. So that just proves that third law. But it is one that's used quite a bit in questions as well. the fourth law. So the log of 1 to any base is always 0. And why is that? Well, it comes back to our indices again. So any number to the power of 0 is 1. So the log of 1 to the base 2 equals the log of 2 to the power of, the log of 2 to the power of 0 to 2, which equals 0. So that's an important law there. And the fifth law as well, very important, and again we'll be using this later on in a question. But the log of a to the base a is always equal to 1. So if the number which you find the log for and the base are the same, then the log is always 1. So the log of 10 to the base 10 is 1. The log of e, or natural log e, which will be to the base e, that equals 1 as well. Again, that's one that's used quite a bit in questions. Sixth law, a to the power of log of x to the base a equals x. So for example, you might have this situation where you have e to the power of ln2, that equals 2, because remember ln2 is to the base e. So I've used that myself in solving problems, so handy law. Another very useful law here is the change of base law. So this is a situation where you might want to change from one base to another to help simplify your calculations. So in this case, the log of x to the base a equals the log of b, which is your new base, the log of x to the base b, your new base, divided by the log of a, the original base, to the base b, the new base. And if x equals b, that simplifies out there to the log of b to the base b, which is 1, remember what we saw earlier, divided by the log of a to the base b. There's a way you can remember that is ABBA, the group ABBA, so that helps remember that change of base law. Can be very useful in problem solving as well. So here's another question for you to try. That's evaluate the log of a to the power of 6 to the base 2. So a little tricky, there's a few things in it there, but one way is to think of, well, 8, but how can that be simplified in relation to base 2? That would be one option there. So I'll give you a minute there to try that question. So from one of our laws there, we know that the log of a number to a higher power is the power multiplied by the log. So in this case, the log of a to the power of 6 to the base 2 is 6 times the log of 8 to the base 2. We can simplify 8, writing using the index form of 2 to the power of 3. We can see straight away then the log of 2 to the power of 3 to the base 2 is 3. And then 6 by 3 is 18. So what looks like a complicated question in the end, once you use the laws and use indices, to say I like to use indices to help find logs quickly. In that case, we solved the problem using a few techniques there. So now I'm going to go through this on the whiteboard, this example. So I'll be switching out of the presentation and going on to the whiteboard to do this. So here we're dealing in base 6, log to base 6. So the question is solve x minus 3 to the base 6 plus the log of x plus 2 to the base 6 equals 1. For x being a real number, now you need to be familiar with the notation because it came up in the example that Jerry showed us earlier, and you have to be comfortable dealing with this notation when you're doing the questions in the Leaving Cert. So in this case, the notation is shown that x is to indicate that x has to be a real number or being real. So remember, Jerry was talking about complex numbers, imaginary numbers, and so on. So it won't be one of those. And it's also saying that x must be greater than 3 in this case. So I've just brought up the whiteboard, so hopefully you can all see that. And I've written out the question again on the top there. So we're going to use 2 of the laws in reverse, if you like. So if we go back to this law here, so this was so here we had the law that said the log of a multiplied by b to the base 6 would equal the log of a to the base 6 plus the log of b to the base 6. So if we see on the left-hand side of the equation here, the log of x minus 3 to the base 6 plus the log of x plus 2 to the base 6 can be written as the log of x minus 3 multiplied by x plus 2 to the base 6. That's one law we're going to use. And then, very importantly, the other law, I'm going to put in one here. So the log of 6 to the power of 1, it's implied, to the base 6 equals 1. So using those two laws, it's going to mean that the left-hand and right-hand side of the equation are going to be in the same format, because currently one side's in a log format, the other is just the number 1. So we can rewrite the equation as follows. Now that's a bit better to deal with. So we see that the log of x minus 3 multiplied by x plus 2 to the base 6 equals the log of 6 to the base 6. Now, similar to how we would have worked with indices, we can actually take this part to be equal to this part. So if you like, we can ignore the log 6 part now. So that's similar to what we would have done when working with indices. So that's an important technique. So we can then say so that x minus 3 multiplied by x plus 2 equals 6. And if we work that out, x squared minus x minus 6 equals 6. X squared minus x minus 12 equals 0. Now it's interesting, Jerry referred to the formula for quadratic equations. So that was that formula here, minus b, sorry, x equals minus b plus or minus b squared minus 4 ac over 2a, where a is the coefficient of x squared, b is the coefficient of x, and c is the final part here, the number here. So using that, we can use that. You can work it out yourselves, but it actually comes down to x equals 4 or x equals minus 3. So if we go again to what our problem asked, it said x must be a real number. Okay, they're both real numbers, but x must be greater than 3. So the solution is x equals 4. So it's important when you're working through these problems that you actually don't leave any ambiguity for the examiner. You write it down. The final solution there is the final or the correct solution is x equals 4. So I hope that gave you some idea of how the laws of logs can be used to solve a fairly tricky problem. So how else would we use logs in problem solving? Well, they are used quite a lot in this situation where you've an x to the y type equation. So for example, if we were given this problem to solve, 10 equals 100 to the power of 1.2x, how would we solve that? Well, if we take logs of either side of the equation, then log of 10 to the base 10 equals the log of 100 to the power of 1.2x to the base 10. And again, using one of our laws we're quite familiar with now, that equates to 1.2x by the log of 100 to the base 10. So again, log of 10 to the base 10, 1, and the log of 100 to the base 10 is 2. So we can then work out x is 1 over 2.4. If we were given this problem where 1 equals e to power 2t, well, again, we take logs either side of the equation, but in this case, because we're looking at e, then we would use natural logs. So we would say then ln, and ln is used always for natural logs. Ln, so it's implied that it's to the base e. Ln of 1 equals ln e to the power of 2t. So again, we bring the 2t down in front of the ln e. So ln 1 equals 2t ln e. And remember, ln e, ln is to the base e. So the natural log of e is always going to be 1. So therefore 2t equals ln1. So t equals ln1 divided by 2. So that would be, they would be two good examples of where logs would be used. So it's not always possible to, when you're doing a problem, to say, well, should I use the log or should I not? It may just take a bit of practice to identify when logs would be used and when they'd be suitable for problem solving. But certainly in these situations, they're ideal to solve those type of problems. Now, logs have come up directly in questions. They may come up indirectly as well. Certainly over the last few years, there was quite a tricky question. We'll see it now in 2016. 2018 it came up, wasn't quite as difficult, but 2016 was tricky. So we're going to go out onto the whiteboard again, to look at the question 2016. So this is the question from 2016. Given that log of 2 to the base a equals p, and that the log of 3 to the base a equals q, where a is greater than 0, write each of the following in terms of p and q. And certainly you would you'd need to be familiar with the law of logs to get this question right. I'll just set up the that's the question again, but I'll write out the terms, and we can use them in solving the. So the terms we were given: p equals log, sorry, just having a problem with my stylus there. So p equals log of 2 to the base a, and q equals log of 3 to the base a. So if we take log of 8/3 to the base a. Now remember from our previous laws in logs, we saw that the log of x divided by y is the log of x minus the log of y. So we can then write this statement as follows. Log of 8, base a, minus the log of 3 to the base a. But we want to get on one side here we have q, so because of log of 3 to the base a is q. But in the case of the log of 8, we want to get that into the format of the log of 2. So you can write, this is where the indexes come in again here. So 8 is 2 to the power of 3 minus log of a 3. And again, from our laws, we know that the log of a number to another power, we can bring down the power, so that equals 3 times a 2 minus the log of minus the log of 3 to the base a. So we have now our statement in a format that we can actually input p in terms of log of 2 to the base a, and we can input q in terms of log of 3 to the base a. So we can finish up by writing the statement as this: 3 times p minus q. So you can see that you would want to be very familiar with the laws of logs to get that problem done. So I'll just write up the definitions of p and q again. P equals log of 2 to the base a, and q equals log of 3 to the base a. So this second part of the question is, what is the terms of the equation of 9 a squared over 16 that equals now in this case 9a squared over 16 that equals log of 3a squared minus the log of 2 to the power of 4. So again, we know that from the laws of logs, the log of x over y is log of x minus y. So in this case, 9a squared is 3a squared, and 16 is 2 to the power 4. Now, this is quite a tricky part of the question here, because the log of 3a is the log of 3 multiplied by a. So again, we're going to use our first law here, which says that the log of 3 multiplied by a will be equal to the log of 3 plus a. But remember, we have to bring down the 2 here. So we'll first write this. A, and these are to the base a. Minus, and we can bring down this 4 here as well, minus 4. Log of a, log of 2 to the base a. So, because this is 3 multiplied by a, this is 2, the log of 3 to the base a, plus 2 times the log of a to the base a, minus 4 log of, the log of 2 to the base a. Now again, remember that in our law there, where we had the log of a to the base a will be 1. So we can simplify this. 2 times log of 3 to the base a plus 2 by 1, which is 2, minus 4 times the log of 2 to the a. So we have it almost done now, because we can see that the log of 3 to the base a is q. So we can input that into the equation. So that's 2q plus 2. And then we can see here that the log of 2 to the base a is p. So that's minus 4p. So that was quite a tricky question. Definitely need to be very familiar with your law of logs, but I think it's a good example of how they're applied in Leaving Cert questions. I think we're almost out of time, so I won't have time to go through another question, but I hope that that's given you some different views on the principles and the applications of indices and logs. Again, it's practice. It's start off with the indices, be comfortable with the laws, then move on to logs. But you can see even here in this question that indices came up and were used within logs. So they are two parts of the one coin. So I wish you all the best in your studies, and I'll be talking to you again in another few weeks for a tutorial on trigonometry, and I hope to see you then. Thank you very much.
Thank you very much, Ed, for that really good talk on indices and logs, and it tied up really nicely with what Jerry was doing earlier. Okay, I think that's all for now for this week. I would just like to say that maybe a really good idea at this stage would be to make sure and do some practicing of those of problems like that from the past papers or from any book. Your school book would be just fine. And I've just put up, I think, have I shared it? I think I'm sharing a link to the Khan Academy, which has got both tutors mention this, and it's got a lot of really good resources in there for maths. So I'm going to finish up now by just saying thank you to the two tutors for this week, Jerry Sweeney and Ed Collins, and we'll hope to see you again next week for the Algebra 1 tutorial. So going to leave you with that, so bye for now.